Welcome to lecture 23. Today we'll be covering the Rayleigh Ritz method. And this is the very lecture we've been waiting for because this is the lecture is going to teach us on how to approximate solution to partial differential equations, to differential equations. Generally speaking, when we try to solve a differential equation, you can just use a closed form solution from a book, a book on differential equations. But that doesn't lend itself to developing a systematic approach in solving differential equations for very complex domains, complicated domains. And as a consequence, today's lecture is starting to give you the stepping stone on how we can achieve that in a successful way. And so the method we'll be covering today is called the Rayleigh Ritz method. And I'll be going through the derivations of this method in this lecture. Let me remind you a little bit about what we accomplished so far. Um, we started with talking about the physical problem. So we already covered the physical problem. And then we talked about the idealization of that physical problem from 3D to bar theory to beam theory. I have not covered plate yet, but we'll be covering that in the future. But we covered the bar theory and beam theory, both Timoshenko and order Bernoulli beam theory. We covered the equations of elasticity very well, the 3D version, and also the bar and beam theories. We covered the strain deflection relationships, the stress equilibrium equations, the constitutive law, and the boundary conditions. We also came up with the differential equations that basically govern the field's equations of elasticity. Now, you could use the finite difference method as one way of solving the problem, but it doesn't lend itself very well for structural problems. And you'll see that in our area of expertise in structures and also even heat transfer, the finite elements is a preferred approach. We use variational forms to develop these differential equations. And in today's lecture, now we're looking at Rayleigh Ritz method as as a way of solving these differential equations. Just to remind you, if I have a 2D heat transfer problem of a square with temperatures prescribed at the various boundaries, and I were to solve this Laplace equation, you can see the analytical solution is not that simple. This is an analytical solution you get at the top. But my goal is not to deal with an analytical solution because it's very limited in application. My goal is to be able to take a problem and turn it into a simpler problem in by we're just taking the domain and dividing into subdomains and into little triangles for which I can try to solve the problem. And the idea is to be able to turn the problem into something more manageable, which is just a stiffness matrix times temperature equals the heat flux, or some forcing function that has to do with heat. And so there I can now invert this matrix and find the temperatures, which I can then plot very successfully. That is my goal. If I can achieve that, I've done a lot. And so for the heat transfer problem, according to the previous lecture, 22, we talked about taking governing equations like this one, and I showed you the procedure on how to develop a functional. In this case, there was a functional that we were able to get, and the functional was this one right here. That's a functional we found. Meaning, if I take this functional and found the first variation and integrate by parts, I'll be able to then recover this governing equation. So this functional actually does a very good job of describing that governing equation, meaning if I find the function t that minimizes or maximizes I, that function t can be found by solving this governing equation. Okay, so that's the one that will minimize or maximize the functional. It turns out that if a functional exists and the system is self-adjoint, then the, the functional is a minimum at stationarity. You can guarantee that. Then I took another governing equation and showed you how to construct a functional. And again, yet again, this is the functional. And if I find the function y that renders I stationary, that function y can be found by solving this governing equation. And if I solve that governing equation, I find y and I plug it back in here, that y is the one that minimizes I for this example. Then yet again, I gave you a third example of another problem. And in this problem, I showed you how to come up with a functional again. This functional, when minimized, basically by setting the first version of I equal to 0, the function u that minimizes or maximizes I, that function u can be found by solving this governing equation. Again, once again, I'm able to find a way of minimizing or maximizing that functional. Example 4, yet again, this is the governing equation. Sure, from that governing equation, I showed you how to construct the functional. And if I'm able to construct the functional, the w that minimizes or maximizes that functional can be found by solving this differential equation with those boundary conditions, which are 4 of them. There's a lot of boundary conditions there. So very cool. Notice how the functional has v naught and m naught, which are basically here, are provided here. And somehow I have to satisfy this, the governing equation, the function w that we select has to be kinematically admissible, meaning has to satisfy these boundary conditions when I solve the problem. And then I went through those 4 examples, and in today's lecture, I'll be covering finally for the first time, I'll be showing you how to approximate the solution to, for example, this differential equation, for example, 4, and then showing you how to solve it for this example, how to do it for this example, how to solve these differential equations. We're going to be doing that today. So, and then this heat transfer problem. So yeah, so why we don't jump in and show you how we do this. It's exciting. It's an exciting day because you've been waiting for this. Let's cover approximation theory. Let's cover approximation theory. The goal that we have in mind is to solve differential equations or partial differential equations using approximation theory. In today's lecture, I'm covering a method called the Rayleigh Ritz. Method. And to me, it's exciting because we're going to be using an approximate method to solving differential equations in a way you have not seen before. If you have taken a class, if you have not taken a class on this, and so what we don't consider functional first. So let's consider the functional. Consider the functional I of wx, comma x equals 0 to L 1/2 EI w prime squared. And let's, just for fun, let's add a spring, a constant spring stiffness K, a foundation of some kind, W squared. And let's apply a load also, minus Q times W twice, oh no, not twice, I apologize, dx. And let's assume it's a clamped condition. So let's assume it's clamped on the left-hand side. And then you have that spring that's distributed like an elastic foundation. Okay. And let's assume there's a load Q applied here, like that. And you should already know how to derive this functional. But let's not worry about how to derive the functional. What I want to talk about right now is how to solve differential equations using Rayleigh Ritz. And so let's first think about what that means. So if I want to find the function W that minimizes I or maximizes I, but we know it minimizes I because the functional exists, number one, but also number two, this represents a conservative deformation process and the loading is clearly conservative. So a functional this functional should be self-adjoint. You should be able to prove that with the procedure I showed you before. Secondly, we can demonstrate that is a minimum at stationarity. But let's determine what is a governing equation that implies it's functional, meaning what is the function W that minimizes I? What is that function W? How do I do that? How do I do that? So to do that, I set the first version of I equal to 0, which we also demonstrated can be done by setting the partial of I evaluated at W plus epsilon eta respect to epsilon at epsilon equals 0 times epsilon equal to 0. We already know how to do that procedure. We'll then first find the first version of I. The first version of I is simply 0 to L EI W double prime del W prime plus K W del W minus Q del W dx equals 0. And so this is the only uh, one here that needs to be looked at carefully because there's a W double prime and I want to get rid of that. So I'll just integrate by parts. I apologize for that. I apologize for that. And I'll integrate by parts in my way, which doesn't mean it's the only way. You guys can do it in other ways. I found this way my students and in general do really well and don't forget what we're doing, which is integration by parts. It's easy to forget what you're doing when you integrate by parts, and this way reminds you what's going on really. So I just integrate by parts. I don't quite like how I made everything so close because those watching the video may not understand what happened there. So let me just put some more space in between if you don't mind. And then we'll be going our way very quickly here in a second. So now I have the bottom term here goes inside the integral always. So 0 to L. And notice how del W this del W factors out. So I'll just factor del W out. And I'll have EI W double prime plus K and then W minus Q and then dx. And then I have the boundary terms that need to be accounted for, which is, and I'll just write it that, I will write all the boundary terms in the long way. So plus EI W prime del W prime, and that's at x equals L, minus EI W prime del W prime at x equals 0. Then we have minus EI W double prime prime del W at x equals L plus EI W double prime prime del W x equals 0. All this is equal to 0. And obviously at this boundary, at that boundary, W is 0 and W prime is 0. So obviously those boundaries are 0. And so in our case, W then is specified at x equals 0. So therefore this goes away because W is specified. This goes away because W is specified at that boundary. W prime and W is 0. And at this boundary, this free end, there's no moment applied. So this is 0. And there's no shear applied. So this is 0. If you were to solve a physical problem, you will know that because you can look at that there's no moment applied there or shear at this end. And so then all the boundaries went away. And so for by the fundamental lemma of calculus of variations, then the governing equation becomes EI W double prime plus KW minus Q equals to 0. And the boundary conditions are given by on the left hand side, these are the boundary conditions. On the right hand side is going to be EI W double prime is 0, and then EI W dollar prime prime is 0 at this boundary here. So we have a fourth order differential equation. So I have 4 boundary conditions. So that makes sense. You should be able to solve it in Mathematica very quickly, or MATLAB, or actually you can, I believe you can solve this very simply by taking the solution to a homogeneous and a complementary solution, plug it in W for EI to the WT, or to the X, and then you can solve it using a differential equations book. But I don't want to do that. I don't. That's the whole point of this class. I don't want to solve this. I don't want to solve this equation using those methods, because those methods are not really useful for very complex problems. They're useful for very simple problems. So with that said, I'm going very clearly, if I solve for W with these boundary conditions that I have, these 4 boundary conditions, and I solve for W, that I plug it in here is the one that minimizes or maximizes I. We know it minimizes I because this is a conservative system. So that is a cool thing about what we're going to be discussing today. So I want to find the function W that really makes that happen. And so let's examine really what's going on. I have this functional, and you have to really kind of think with this me here, because this is not your typical function. I'm going to be talking about a very abstract point with this picture. So that's why you need you to pay attention to what I'm saying, because it's an abstract way of explaining something. And so you need to just pay attention. So this is a functional I, which depends on Wx. So this functional I depends on a space of functions. This is a space of functions of W. It could be a bunch of different functions. There are infinite number of functions here. There's infinite number of functions. Infinite number of functions. W of x. Many of them. Some of them could look like sinh, cosh, sine of x. A bunch of them. Infinite. It could be a linear combination of functions. It could be ax squared plus bx plus c. There's a bunch of them here in this plane at the bottom. This plane at the bottom is made up of functions of W. Do you agree that there's a function W, there's a function W that minimizes this functional? And that function is this one right here. Somewhere here. This function is the one that minimizes I. And that function, W, can be found by solving this differential equation with these boundary conditions. Okay? So we know that's the case. And this space of functions is a space, this space of functions W is a space of admissible functions. Okay? So what if I don't really want to find that function? What if I don't really want to spend my time finding this function because it's painful to really have to solve this? You know, I don't want to put the work of solving this differential equation. We do have mathematicians in our class, so perhaps they can quickly do it for us. But what if I don't want to do that? What if I don't want to spend that time? And so to achieve that, then I will say, okay, well, you know, instead of doing that, we will do something else. Let's pretend that there's an approximate solution then. So let's instead we will try to find an approximate solution. That is in a space of kinematically admissible. It's a feasible solution. By considering a set of functions so let's make W tilde be the approximate solution to the problem. So Wx is the real solution to the problem. W tilde x is the approximate solution to the problem, and it will satisfy. We're going to make W tilde x to satisfy the essential boundary conditions of the problem. We're going to make sure it's kinematically admissible. We're going to make sure is a function that's physically physically possible. And what I'm really saying there, let's go back to the idea of finding a curve that minimizes the distance between these 2 points. The solution is a straight line. We know that. That was a little bit horrible on my end to draw that incorrectly. If I'm going to take a function w that's maybe a polynomial, if I want to find this function w, which is approximate, I want to make sure that at least satisfy those boundary conditions. I don't want it to just go hanging with no boundary conditions. So I want to make sure that my approximation w satisfies, is kinematically admissible and satisfies the essential boundary conditions. And because this may not be a structural problem, it could be a heat transfer problem. Let me remove the kinematically admissible. It just needs to be admissible, period. It needs to be admissible. And to make sure that happens, you need to satisfy the essential boundary conditions. So I'm going to assume that W tilde x is going to be some function that I select a priori, maybe a polynomial, phi naught x, plus summation from I1 to n, ci phi ix. And I'm going to call these guys, this one here, I'm going to call it the Ritz basis function. And these phis are basically polynomials I will select ahead of time. Maybe it's x, x squared, x cubed, so forth. Something like that. And the only unknowns to the problem are these coefficient c. Only unknowns. And this polynomial here will be either 0 if all the essential boundary conditions are homogeneous. And if they're non-homogeneous, then it will be a polynomial strictly developed to this polynomial phi naught is developed simply to satisfy, it's a polynomial selected. It doesn't have to be polynomial, it can be a function. So let me just say function selected to satisfy, oh my goodness, sorry about that. To satisfy the non-homogeneous boundary conditions. Essential boundary conditions. So I'm going to come up with an approximation function. Bottom line, this phi naught will be known, don't worry. These phis, we'll select them smartly. So what is the only unknown? Now is the CIs, which are just constants. And so what I've done then, if I look at my graph to the right, this functional I depends on what function W I select. And so I construct this this surface comes out as a quadratic functional. This is your quadratic functional. And we know a minimum exists if the system is self-adjoint. So we know there's a minimum, and that minimum is this one. That's the exact solution. This is the exact solution to the problem. If in this space of functions, this is a space of functions, I select now a W tilde x. This W tilde x will be selected. So then if I selected that a priori, what I've really done, I have constricted that space. I've constricted what W tilde x is. So this W is the W tilde x that I selected. That's a space of functions. when I look at the projection of W tilde x onto the surface, this functional, then now my minimum can be found. And so then what I notice here is that this is the error between the exact solution. That's the error between this approximate solution. Well, this represents the error. And as I increase the number of unknowns n to infinity, this error will go to 0 as n goes to infinity. In other words, I found a potential way, a very smart way, a potential way of perhaps solving this problem in a different way. So W tilde x is an approximate solution to this differential equation. And so perhaps what I need to do then is substitute this approximation. I'll substitute that approximation into my functional here. And if I do that, perhaps when I find the stationarity of I, I've actually solved the differential equation indirectly, which is insane. It's an insane idea. Okay, so let's look at what I just said in a graphical format to make sure you understand what I just said, because those words I said are extremely important to this class. This is the functional of interest that I came up with. And this idea that we're discussing, to me, is an amazing idea. If I want to find the function w that minimizes I set the first version of I equal to 0. That will give me the governing equation I just showed you earlier. So let me type it here. So you remember, and the boundary conditions were w at 0 is 0, w prime at 0 is 0, and then ei w double prime is 0, and e at L. So let's not forget that. This is horrible. I apologize. So yeah, so if I solve for W here, I get the exact solution. And this W is the one that minimizes I. But I don't want to solve for the exact solution. That's too much work. So let's instead approximate the solution with W tilde x. And so W tilde x now is made up of a polynomial that I know plus summation of I equals 1 to n, Ci phi I of x, say. And these C's are the only ones that I do not know. So, doesn't it make sense to you that if I plug in W tilde into here, and then I render the first version of I tilde now, because if I substitute W tilde here now, then this becomes a different function I tilde. So don't you believe that if I take the first version I tilde, now I tilde only depends on those C's. Let me show you so you can see for yourself. Let me plug it in. You're going to see. So now this I turns into something else. It turns into this. You tell me if you agree with me. I think you're going to agree with me. And if you don't mind, well, I'll just put it here, but I'll put the summation, but it looks messy when I do that. And that's squared. And this is from 1 to n constants. Sorry about that. Don't you agree? Don't you agree that when I plug in this approximation function W in here, and I substitute anywhere I see W, I put in W tilde. So I put that whole thing in there. Don't you agree now that the function I now depends on C1, C2, Cn? Clearly does, because phi naughts, these phi i's are known in advance. There could be sine, cosine functions. They're given to you. So then the only unknowns are really C1, C2, C3, C blah, 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 Cn. So therefore, now my functional I became just a regular function from calculus. Function I just became a function of C1, C2, Cn, blah, 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 blah. So therefore, the first version of I then becomes just a partial of I respect to the coefficient C1, del C1, plus the partial of I respect to C2, del C2, plus blah, 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 until partial of I, Cn, del Cn equals 0. Therefore, for any variations of del Ci, del C1, del C2, del Cn, for any variations, then partial of I respect to Ci or Cj, let's say Cj, equal to 0 for j equals 1, 2, blah, 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 up to n. How many equations I have? N. How many unknowns I have? N. So then I can plug in those C's into here, which means I found the approximation function W that minimizes I, but at the same time, by doing that, I have done and conducted a mathematical miracle. I've also found the approximate solution to this differential equation. Let me explain one more time why, to put everything together into pieces. This functional I represents a particular system, say. That functional I, when minimized, implies that I need to solve for W to find the one that minimizes the functional I. Well, that is the one that solves this differential equation, that satisfies these boundary conditions, okay? But no, I don't want to spend time solving for the exact solution. That's useless to me. That's actually a waste of my time, because I cannot solve anything more than just a simple problem. It's useless. In physical problems, I need something much more useful. So what if I now approximate the solution with in advance, I select these polynomials in a smart way, and I saw, and then the only on, or it's not polynomial, maybe it's cosine and sines, and then I will then make these the unknown coefficients. I plug in that approximation function into W tilde with these unknown coefficients, and when I plug it in, I realize now that the only unknowns are C1, C2, Cn, and so forth. And so therefore, my functional used to be a functional is no longer functional. Now that function only and only depends on these coefficients that are unknown. And these coefficients are not functions. These coefficients are just regular numbers. Therefore, I just becomes your typical function from calculus. Therefore, when I first find the first version of I get this. And therefore, the partial of I respect to Cj must be equal to 0, because each of these unknowns need to be linearly independent. And so as a consequence, I have n equations, n unknowns. I can find C's, these C's. And so therefore, this approximate function, which is the one that does the best possible job to minimize I, is also the one that does a great job of approximating the solution to this differential equation. And that's a mathematical miracle. So to me, it's an exciting time, because we found a way of approximating solution to differential equations in a very unique way. And just to remind you, the phi i's will be selected in a smart way. Phi naught will be selected in a smart way. Phi naught needs to satisfies the essential boundary conditions if they're non-homogeneous. For example, in our problem, these are the essential boundary conditions. if any of these W's were, if this W naught was 5, that's a non-homogeneous boundary condition. And so this phi has to satisfy that particular boundary condition. And I'll show you how to go about that in a couple of minutes. So to me, this is very exciting. Let's now discuss how to select this function in a smart way. So phi naught, I already discussed, it has to satisfy the homogeneous boundary conditions and the non-homogeneous boundary conditions. Ritz basis functions. I apologize. A, phi naught must satisfy the homogeneous form of the boundary conditions and also the non-homogeneous form. B, phi i's are selected in a smart way. They need to individually satisfy the homogeneous boundary conditions. And what I meant to say here is non-homogeneous. I apologize. C, the phi i's need to be linearly independent. In other words, if I were to have this equation put together, the only solution has to be C1 is 0, so all these need to be equal to 0. That's the only way you can verify linear independence. Example, if I were to select, and also I forgot, fourth condition, they need to be complete set of phis. So say, for example, I have phi1 of x is 1 plus x. Phi2 of x is 1 plus x squared. Phi3 of x is 1 plus x cubed. You can then check later that C1 phi plus C2 phi 2 plus C3 phi 3 equals 0. You can check later that the only solution C1 equals 0, C2 is 0, C3 is 0. That's the only solution to this, okay? And so, yeah, so it needs to also be complete. For example, if phi1 is x, you definitely want to have a linear set. You don't want to jump to x to the fifth. You want to have a complete set. So x squared makes sense as the next one. Phi3 is x cubed and so forth. You want to be smart about how you select the functions also and making sure they're complete. If you have a complete set of boundary, if you have a complete set and it satisfies so far A through C and is complete and is linearly independent, you can actually show that the limit as n goes to infinity, the number of terms goes up, that the functional I, in this case I use I, the functional I, which has approximation function inside, is going to approach the exact solution. And I won't go through a mathematical proof, but it's going to approach the exact solution. It's going to converge to the exact solution, which is actually quite exciting if you think about it. And so for completeness, with respect to the integral over the domain, we want to make sure that to guarantee convergence, you have a complete set of polynomials being considered. You also want to make sure that the Ritz basis functions do not, Ritz basis, Ritz basis function. We want to make sure that they do not impose fathom boundary conditions. What do I mean with that? So if I have a beam that's clamped and I apply a load, I expect it to bend this way. So one of the functions cannot be possibly this one because that's imposing a slope here that does not exist. So you want to be careful about the functions you're selecting that they do make sense. You also want to make sure, ensure W tilde of x, the approximation function, is sufficiently differentiable. Differentiable, meaning is sufficiently smooth, if that makes any sense. What I mean with that is that if you look at I for our example, the highest order derivative is second derivative. So me, if I put a linear function in here, I get 0. So I have a square of a 0 value. That's not acceptable. The lowest order that can possibly put in here is a quadratic function, because a quadratic function makes total sense. A quadratic function gives me, yeah, a quadratic function works out. You can see that there. Quadratic function will give me a constant value, so a constant value can be integrated. So that makes sense. That's the lowest order polynomial you could use. If I use a sine or cosine function, you can do infinite number of derivatives. Is always sufficiently smooth. So that one also works out very nicely. So yeah, you can see here that that's the way it works. So why we don't look at the example of the very example I looked at today? Why we don't look at this beam over the elastic foundation with those boundary conditions and see how we will approach it? So let's go through an example, application. So I have a clamp beam with a distributed load, Q, on an elastic foundation. And the governing equation for this was found to be EI double prime plus KW minus Q equals 0, with the boundary conditions of W not equals 0, W prime is 0. And finally, I have EI double prime is 0 at L, and EI W triple prime is 0 at X equals L. So let's try to do this problem, and I want to use both Mathematica and I want to use Mathematica for the exact solution, and I also want to use this Ritz method to see if we can get it to work. It's the first time I attempt this in class, but I think it's worth it. So let's first come up with a polynomial. So let's start the first step, step 1. In this case, I want to use a polynomial. You can use a sine or cosine function, but I want to use a polynomial. So step 1, use a polynomial. But the first step is to satisfy the essential boundary conditions. So I said before, W tilde x equals phi naught plus summation from I1 to N Ci phi I. I want to come up with these guys. So we'll use a polynomial, but before I figure out the form of that, I need to first kind of satisfy the boundary condition. So W of X, I have two boundary conditions that are essential, and W tilde X has to satisfy it. So as a consequence, I'll start with a quadratic function because it will leave me 1 degree of freedom to figure it out. And so I get that W of 0 is 0, so C naught is 0. I also get a W tilde prime at 0. I have to evaluate that, so that's going to be C1 over L plus C2 X divided by L squared. Evaluated at X equals 0 is 0. That gives me C1 is 0. So right now, what this is telling me is that my approximate solution to the problem is going to have this form. It's going to have W tilde of X equals C1 X over L plus C2, I'm sorry, is going to have C2, it's going to have this term. It's going to have only this term. These terms are 0. So I'll just start over. So I'll say it's A1 XL, A2 is XL squared, A3 XL cubed. I want a complete polynomial, so I'll just do that. Just notice here how each of these satisfies, and again, I made an error, so that's squared, cubed, fourth, and so forth. I made a mistake because these terms were 0, and I know that my approximate solution has to satisfy the essential boundary conditions, which are this. These are my only essential boundary conditions. You can verify it. If I plug in W tilde at 0, you'll see that this works. I get 0. W tilde at prime at 0, I also get 0. You can check that it works. So these are very good one to use. We could also, for the sake of doing a realistic problem, let's use aluminum. So let's say the length of the beam is 50 inches. I'll say the modulus E is 10 E6 or 10 MSI. That's aluminum. And I'm going to use a moment of inertia of 1 over 12 BH cubed, so 1 inch height, 1 inch height. Sorry, the width is 1 inch, the height is 1 inch cubed. So I just keep it simple. So I get 1 over 12. And then what else can I define to make everything very smooth? So let's come up with K of, say K is, say 1/10 of E. So let's say it's about 100,000. And say Q is a load that I applied of about 1,000 pounds. So why we don't go ahead and go to Mathematica and try to solve this there. So my first step before I go there is to substitute. I want to substitute this into, I want to substitute that into the functional for this problem, which is this one. So that's what I want to do. So let's do that. So I did make a mistake. I tilde becomes I as we increase the number of terms of her n. You get the exact solution. You get the exact functional. So that's what's going on there. Why we don't go to Mathematica is an exciting problem and try to do it here. Why not? Why not try to do it here? So I recognize I have I here and I here to the left-hand side, so I apologize for that. So one of the things that's very helpful if you don't know how to use Mathematica is to you have the help manual here. So you have the Wolfram documentation, and say you don't know how to solve a differential equation, you can quickly look it up. That's what I do. So I just type differential equation, and it will just give you like, okay, it tells you it's desolved, but they will also give you examples, I believe, like here, it gives you examples. So, sometimes what I do, I just copy and paste it and just borrow it. And if they have one where they give you boundary conditions, could be very useful. Yeah, so they have some examples here. You can see here they have the boundary conditions, and they tell you, these are the functions I need to solve for, and so forth. So yeah, they have some very neat examples actually here. So why don't go ahead and just type the example problem here directly, and first I want to solve it exact. What is the exact solution? So I don't know if I'll be able to get it. Why not try it and see what happens? Um, I'll make everything W to keep it consistent. Okay, so I have that so far, minus Q, and then I will make this equal to 0. Secondly, I should define some variables. So I define K to be, can somebody tell me what K was?
100,000, you said?
Thank you. So 100,000. And I like to put semicolons to keep everything compact. I believe, is just 1 over 12 because it's 1 inch height, 1 inch. And then length is 50. And I think that should be enough to survive. And let me just define EI. So mathematics is going to have a problem with this I. So let me just call it double I for inertia. If you don't mind, EI is going to be E times double I. This big E. And it may have a trouble with that too. So let me just make a double E here. Because E is exponent maybe. So I don't know if it's true, but I'll just do that for now. So that's what I get. To solve it, I believe that we're almost set. All I have to do is just do that and add the other boundary conditions, which are basically, if you don't know, actually you can do desolve like that, and it will tell you exactly what needs to be entered.
Do you need to put EI in front of your W?
Yeah, I will do
Prime,
that.
prime, prime, prime.
Yes, thank you. So EI, and then you can see here, it tells you how to go about that. It kind of tells you. Um, I'm going to go ahead and put the boundary conditions as well. So for example, W at 0 is 0, and W prime at 0 is 0. And then I could put EI if I want to, but if you recall, the boundary condition was just W prime is 0. I can just cancel out EI and just put W prime. So I just do that, if you don't mind. And that was at L, which at this fine at 50, that's 0. So this has very easy boundary conditions. You can see that here. Very simple boundary conditions. Um, And hopefully, when I do this, I haven't done this for a while, so be patient with me. Perhaps it's not going to solve it, but we'll try. And it did. It solved it very quickly, actually. Um, it looks awkward with these queues. Maybe I didn't define queue, I guess. The loading was provided, and how much was it? Q?
1,000 pounds.
Yes, 1,000 pounds. Let's go to 10,000 pounds or 1,000 pounds. Just keep it 1,000 pounds. Um, Let me put dot everywhere because it makes it numerical that way. I don't want to carry extra stuff. Let me put semicolon, which suppresses the output. So I'm doing my best to explain everything at once. I apologize. So you can see here, it plotted it. It plotted it. Here's, it didn't plot it. I can plot it if you want, but this is the solution that we get. Um, and so, what if I want to plot the solution? So let me make this equal to some value solution exact, let me call it. So that's my solution exact. I'm trying to do my best to explain the procedures that I typically use. So I will do, okay, solution exact. Let's try if it works. And I want to select this one here. And to make sure I selected the right one, I'll select, whoa, sorry about that. Let me just delete this if you don't mind. Okay. Solution exact. Okay, let's say it. Let's see if this selects it. Okay, still didn't select it. I have to select another there. And then I think I have to select the second one. So I usually kind of do trial error. I don't, I just follow the examples typically. Now I can go ahead and plot this solution over the domain, which is 0 to 50. The beam goes from 0 to 50. Let's see if it plots it. Hopefully it does it. And it looks like it has a very strange behavior um, here towards the end. So I don't expect my exact solution to be the best, to be honest. Perhaps my spring constant is too high. Let me make it smaller because that looks very, very, very pronounced. And I want to be able to do something where you guys can see, um, something that kind of makes sense. Yeah, that's more manageable. Like you guys can see what's going on here. That's a lot of deflection. That's about 1 inch. So I'll fix the PowerPoint. I use 1,000. I could go lower, but you can see it's clamped, and obviously the loading is causing it to bend in a very interesting way. So yeah, that's the exact solution. Uh, yeah, hold on. So so what I did there was to select the solution. So this solution came with brackets, and Mathematica puts in those brackets. So all I'm trying to do is select this particular portion of the solution. Another way that you have is to copy that and just paste it here. That's another way that I've learned how to do. You can paste it here and then just plot it, which actually looks more correct. Perhaps I did this incorrectly. I'm supposed to copy this whole thing up to there, I believe. So copy that and paste it here. And that's how the beam deforms. So you can do that, or you can just do the way I did it, which is just trying to select the element within the solution. Okay? So now that's the exact solution. I'm not convinced I'm going to be able to work it. So hopefully, can somebody check that I didn't make a mistake here? This looks good so far. I don't see a problem with my. Yeah, everything looks good to me. Okay, everything looks good there. So what we're going to try to do the exact solution. Now, I select a problem for which is more complicated. If I didn't have any k, for example, and no k there, actually, just make k 0, for example, you'll see that it's going to behave differently, and perhaps it makes more sense for me. You see, it's a quartic polynomial. That's what you would have gotten from mechanics and materials if you did it. Let me just do it my way so that I don't have to keep typing the solution. All that's doing is selecting the solution to plot it. You can see here the beam bends. I mean, of course, that makes sense. So, okay, let's now try k over 1,000. Go back to that and solve it. And then I get the solution, which looks weird. Sure, is a beam on an elastic foundation. So that's exact solution. Okay, and now I'm going to go with approximate solution, which to me is exciting because look how messy that looks like for a simple beam. Imagine more complicated problems. So let's plug in the functional. Functional, let me call it, and the functional is going to be the integrate 1/2 EI W approximate, um, and is the second derivative of that respect to x. I think that's how you do that. Let me first define W approximate. I say it was going to be A1 x over L squared plus A2 x over L cubed plus A3. Let's add us maybe a couple more terms just for fun. Maybe add one more. Why not? I can do it, right? It's easy to do. Let's add 4 terms. Maybe it's overkill. So that's the approximate solution I'm selecting. It satisfies the boundary conditions. You can check it yourself. For example, W, so let's evaluate this. W at x0 is 0, and W, and the first derivative of that evaluated at x equals 0 is 0. So that it works really well. You can see that happening. So, okay, so this works. So the second derivative squared, I apologize, plus 1/2 k, and then I have now the first derivative. So I'll just borrow this so I don't have to type it again. No, there's no derivative. I apologize. No derivative, just squared. That's it. Minus q times w like that. And we're integrating that between 0 and 50. So that's a functional. I think it looks good to me. I think this matches what I have here as functional. I don't see a problem. That's how you integrate the Mathematica. I'm going to do a full simplify, so everything looks very nice and simplified. That's a way that it just takes all the polynomials and put them very nicely. You can see here. Well, he tried. He tried to bring everything together, not quite, but that's fine. That's a functional I got. Sure. Now I will go and apply. Now I have 4 equations I need to solve because I have 4 unknowns: A1, A2, A3, A4. And if you recall from the PowerPoint, here what we want to do is set the first derivative of I respect to each of the coefficients and set it equal to 0. That's how we want to go about that. So I apologize for that again. Let me go straight to what we're here trying to do. So let's find the derivative. So, I like doing it this way. Equation 1, you can be more careful. I'm just going to do it step by step so you can see how it's done. So functional with respect to A1, that's equation 1. Equation 2 is functional. And, I should just make it equal, not like that. I apologize. Equal. Equal. That's my second equation. Sorry. My first equation is setting this equal to 0. Sorry. My second equation is taking the derivative of the functional with respect to A2. And again, I like to do it step by step to see so that when you're doing the exam, you can type it out step by step. Equation 3. I don't want people to be doing everything by hand. It's a lot of work. And instead of just typing it, you can just copy and paste and switch everything to A3. And that's equation number 3. And I'm just doing it as quick as I can, so I'm not wasting time, but also trying to explain the steps. So equation 4, and there's a problem. Equation 4, I guess I don't have it. Oh, I have a problem. I have a problem. This should be A4. I apologize. So this needs to be redone here. I have to redo that. Okay. So I took the derivative of the functional with respect to A1, A2, A3, A4. So hopefully that looks correct. You can see it's a linear system of equations on A1, A2, A3, A4. The equation 1, 2, 3, A4, A1, A2, A3, A4 is a linear system of equations, which is amazing. Because when I plug it into A1, A2, A3, A4, that'll give me the approximate solution that minimizes I, but also gives me the best approximation to the differential equation, which I think is very neat, to be honest. So, okay, now I forgot now how to solve. Okay, I'm going to pretend I forgot how to solve linear system equations. So I just type linear equations and perhaps linear solve. I guess it tells you how to do it. Uh, I think solve, so maybe I should type solve. Say I forgot how to do it. Um, let's see. Let's look for the function solve, maybe. Attempts to solve the system of equations. Okay, so examples. Say I forgot how to do it. By the way, I do know how to do it. I'm just pretending so you can see how I go about it. Okay, that's a system of equations right here with inequalities. You get fancy there. So yeah, looks like I know how to do it. So if you forget, you can also do solve like that, and kind of tells you how to go about that. Let me try. Maybe I don't know how to do it. Let's try equation one, equation two, equation three, equation four. Okay, and I want to solve for A1, A2, A3, A4. Let's try, no guarantees. Oh, I found the solution. Let me call this approx solution, and let me evaluate my approximate solution, W approximate, to be equal to W app, and I want to evaluate it to because if I look at W app by itself, it's like this. So I want to evaluate W app, evaluate on this approximate solution. So to do that, again, I just try to play a little bit of just to see if I can get these extracted out, these arrows extracted out. Or let's see if it works. Let's see if it works just by itself. I'm going to evaluate this. Let's see if it works. Okay, so clearly I found the approximate solution. So approx solution is this. I found it, but it has this issue of it has this bracket. So I'll just do this to see if it goes away, and it went away. Okay, great. So I found my approximate solution. It goes up to a fifth order polynomial. So now I can plot this solution with the approximate solution and see how it compares. I don't think it's going to compare great because it's a really a weird problem. It is a weird problem. I will confess. You know, not too shabby. My approximate solution is within probably. It's not too shabby. If I increase the order, it probably won't do that bad. But this is my approximate solution. Um, you can see that there compared to the exact solution. And I can then look at maybe replicating this with a k. Say I want to replicate this now for, let's do a second example. So second example here, second example. And let me just do the second example because I want to show you what happens when I put a value of k of 0. Okay, fine, I get this, sure. Same thing there. Um, Clearly something's wrong because that's not, okay. Yeah, that's my solution. This should be deleted. And then my exact solution looks, I apologize again, it's not sure what's going on there. Sometimes what you need to do is to clear the kernel, but that looks like it works. And then let's look at the approximate solution for the same problem. You can see the first derivative is 0. And then now the k is 0. So let's see if we can get it to work. Let's see what we get here for the approximate solution. And I solved it now. And that's my approximate solution. And boom, the solution, the exact solution matches the approximate solution. Very cool. So that demonstrates how we can do a mathematical exact solution versus approximate solution. I'll provide those files so you can work it and you'll be very successful doing it. Why we don't look at a more classical problem of a beam? And you know the solution to this problem, so it's not a problem. A beam under an applied load P. And pi for this problem is pi of W of x. Let me be very clear about what that is. is integral 0 to L 1 half EI W double prime squared dx. There's no Q in this case, and there's an applied load at the end, which is PW times L. You can derive this. We've already derived this several times in this class. But let's see how we will approach this problem. It's a clamp beam again, so W at 0, 0, W prime at 0, 0. And you're going to find when you look at the boundary conditions that EW double prime is 0, and you'll find that EIW triple prime is P. You'll find that when you do it yourself. So if you were to find the exact solution to this problem, you'll find that the deflection, you will find the deflection to the problem. The governing equation to this problem is actually EI W double prime equals 0 with these boundary conditions that you see here. And if you solve it, you can solve for the deflection W. Let's say I want to use the exact solution to the end deflection, which I used Castigliano's theorem before, so that's why I like this example. W at L, let's say is, you're going to find is PL cubed over 3I is what you will find. That's the exact solution. Using order Bernoulli beam, which is literally solving this governing equation. So you don't have to be expert in mechanics of materials. If you're a mathematician and I gave you this governing equation with these boundary conditions, you will find that that's the deflection at the very end. But you can actually find the deflection on the whole thing. So we can substitute now an approximation function, and let's assume an approximation function of A naught. Now I have two essential boundary conditions. So let's say A naught A1x plus A2x squared. So we can then figure out what the form of the polynomial should be. And we found earlier, through the earlier example, that a good approximation to this problem is A naught W tilde A1 x over L squared. And I'll just do two-term approximation. Why not? And you will see that this one satisfies the essential boundary conditions accurately and correctly. You can see that yourself. Very clearly satisfy these essential boundary conditions. So we're good to go. So now I can plug in that into pi, but why plug it into pi if I can actually do it in Mathematica? I could do it in Mathematica or I could do it here. But okay, let's set up the problem here and then we'll do it in Mathematica. So pi W tilde of x equals 0 to L 1 half A1. Now I have EI W tilde double prime squared dx minus P W tilde at L. So why we don't use Mathematica really quickly and just do it there, so we're not doing it by hand because it's not necessary. Okay, so I'll just do it here. I'll create a new functional. And actually, I want to borrow a lot of this stuff. Why not just borrow half of this stuff? It's probably correct anyway. So these are our next example here. Why not, right? So let's just borrow all of that. And now we're going to call this example 3. I'm going to be moving very quick. So if you're in YouTube or you're at home looking at this for the first time, I encourage you to slow down YouTube to half X because I don't want to spend too much time on this. The governing equation now is K is 0 and Q is also 0 in this example. But the boundary condition changes. Now, the boundary condition is that we have a cantilever beam. Let me erase this because I don't want to confuse anybody. The boundary conditions are that, yeah, so that's the governing equation, K is 0, Q is 0, W is 0, W prime is 0. On the right-hand side, there's no moment applied, but there's a shear applied. So I should just make this EI with a load applied P. You will find this through calculus variations that EIW triple prime is equal to P. When you first find the first version of I that I had, you will find that. Let's apply a load P of some kind. So let's call P equals 1,000 pounds with a semicolon, so it suppresses the output. And then this is what I get for the exact solution. So let's just plot the exact solution there. That's what we get. We should be able to check that it's PL cubed over 3EI. We can check it quickly. Um, so let's check it to see if I match the solution here. So we said so P times L cubed over 3EI. It should give me, well, that's a large deflection. Um, it doesn't seem right that P times that is 10 to the 13. Oh, I know why, because I need to parentheses like that. There you go, get 50, and you can see here's about 50. So that's correct. So if you plug in x of 50, you should get the exact solution, which is that. So that matches your hand calculations. Let's set it an approximation function goes up to the fifth order. Let's see what happens. In what I did in the PowerPoint, I went up to the third cubed. But let's see what happens if I did that for this problem. Uh, this is what I get. This is what I get. The functional, I can leave the, actually I can keep the functional the same. The only difference, K0, Q is 0, so that will be taken care of. Now, outside of the integrate, I have to have a minus P times W app evaluated at, um, it needs to be evaluated at X equals L. Let's see if it allows me to do this. It may not allow me to do this. So we will see if it lets me do that. Otherwise, I have to do it separately, that term. In my potential energy, the integrate, my functional had that. So that's why you see that there. Let's see if it let me. If it doesn't let me, I may have to do this outside of mathematics, of the functional. Well, it didn't complain. It did complain, but if it's wrong, then I'll go back and do this term separately and add it here. So then equation 1 is that, equation 2 is this, equation 3 is that, equation 4 is that, and then I solve all equations. You can see here A3 and A4 is 0, so that looks good so far. The approximate solution is this, and, well, my load is applied the wrong way, so this should have been plus. That's the only error that I had. And if I do that, it's actually minus here is what I had in my notes in PowerPoint. So that is correct. So this is correct, actually. It was this boundary condition is wrong. So when you actually do it in calculus of variations, you will find it's minus P, not plus P. And guarantee that you're going to get this pointing upwards. And when I plot this one now, the approximate solution matches the exact solution exactly. And so I want to point something very exciting that just happened. My exact solution matched the approximate solution. Why is that? Because in the space of functions that I'm considering, it happens to be that the approximate solution I selected has polynomials, and that those polynomials are the representation of that exact solution. So in our case, we can get that to the exact solution directly because the space of functions I selected contains polynomials, and the exact solution is a polynomial. You could also use sine and cosine functions as well. I think it's worth doing an example where um, you can get a better understanding of how to deal with it in homogeneous boundary conditions. Um, I think that could be very helpful in demonstrating, illustrating what we're doing. But for the sake of expediency, let me cover just one more example so you can see how this could pan out. Another example. For example, I have a beam, and that beam has a load applied in the middle, P. So we can assume an approximate solution, just a simple approximate solution. That I'm not going to even add a lot of terms, but you can. It's C sine pi x divided by L. And we can add another term just for fun, pi. Let's just do one term. This term works because W tilde at 0 is 0 and W tilde at L is 0. So it's a great approximation function because it satisfies the essential boundary conditions of this problem. It is a great approximation to this problem. And so in these examples, the potential energy for this system is 1/2 0 to L EI W double prime squared dx minus PW at L half because the law is applied now half point. And then if you render pi stationary, that'll be the derivative of pi respect to C1, del C1 is 0, and so therefore pi respect to C1 is 0. You can do this quickly in Mathematica, and you'll find that the coefficient C becomes 2p L cubed over EI pi to the fourth. And then so you find that the approximate solution to this problem is W tilde x equals, yeah, so you just get this plugged in here, C sine pi x divided by L. And so that illustrates this particular problem. I think it's an exciting problem. I want to do one more problem before we go, and I'm going to record another lecture on this Rayleigh Ritz, kind of summarizing what we learned. But let's choose a heat transfer problem where the boundary conditions are essential, but they're inhomogeneous. They're not equal to 0. Let's look at that so you know how to deal with that. And this is the functional of concern. So I'm not going to go through the whole solution. I'm going to just show you the steps in how to set it up. A is a constant, K is the conductivity of the material, H is a heat transfer coefficient, and TF is a film coefficient. So I think it's a good problem to look at. I'm going to try to transfer this to the next page. And if I mess up, I may ask your help to kind of capitalize in the fact that you have it in front of you. Heat transfer problem. And I'm going to try to write a functional. I'm going to change the sign on that functional to make it more convenient. But I believe, I'm going to say the length. So I'm going to say this is x at 0 and this is x at L. So there's a wall. That's your wall here. And then this condition is specified. And it's known as T naught. And this condition is specified. The temperature at this other side of the wall is specified as TL. And so what I'm going to do, I'm going to plug it in. I'm going to plug in 1/2 Ka, the functional, I'm sorry, the functional was Ka T prime of x squared. I believe that was the case. Plus, and then I did forget, so can somebody remind me? And make everything positive sign for me. Can you guys hear me? Okay, I guess I will have to do it myself. So let me just do it quick. I got that term. I need to do minus 1/2 HT squared. And then have the minus sign here. I think it was like something like this. And I'll check it. I apologize for those watching the video and getting dizzy. So this is what we got for this problem. Yeah, so I think this is a good example of what we're doing. And in fact, this problem does not represent this problem, so I apologize. It's more of a tube, it's more of a tubular structure of some kind, which is embedded in a fluid with temperature T film. And this bar here, we have temperature specified here and here. And those temperatures are T naught and TL. You can verify very quickly that the essential boundary conditions for this problem are anything specified on T. And so I need to somehow satisfy that. So why we don't come up with an approximation theory for that? We will use Rayleigh Ritz. we cannot use a constant value because a constant, the derivative of a constant gives you zero. Zero squared is not very useful. So at a bare minimum, it needs to be linear. Linear may not do that great, so we could use quadratic. But that's beside the point. Somehow I have to make sure that the approximation theory, approximation function, satisfies the essential boundary conditions. So I have to make that happen. So t tilde of x, and since I have two essential boundary conditions, it has to satisfy both. So let me leave one open for now. C1 x over L plus C2 x over L squared, and figure out how I can make that happen. So t tilde at 0 is T naught. So that means that C naught is T naught. T tilde at L is C naught plus C1 and plus C2, and that's TL. So yeah, so somehow I have to make that happen. So let me solve for C2. So C2 is TL minus C1 minus C naught. TL minus C1 is I apologize. C1 minus C naught, which is T naught. So then my approximation function looks like this. T tilde x equals um, T naught, and then C1, I'll leave it alone for now. And then C2 was found to be TL minus T naught minus C1 x over L squared. And we should check it before we continue. So if I plug in x equals 0, I do get T naught. If I plug in x equals L, this becomes 1. This becomes 1. The C1 cancels out. The T naught cancels out. I get TL. So looks like I didn't have any math errors. Now I have to factor C1 out. Let me factor C1 out first. And when I do that, I'll get this. Okay, this is what I get. So this is my phi naught that I was talking about earlier. And this is the form that I need for my approximation theory, the phi i's. But that's just phi 1 in this example. So you can see here that then the approximation function should look like something like this. T of x, I already say is phi naught of x plus summation of c, and let me use a different variable. Let's call it ai, phi I from 1 to n. So a good suitable approximation is phi naught TL minus T naught x over L squared plus T naught. So that's my phi naught right there. Plus, and now I can add terms. A1 x over L minus XL squared. Plus, I can add more terms too. A2 x over L squared minus x over L cubed. And then continuing on. You want to make sure that this term, the phi naught term, satisfy the inhomogeneous form of the boundary conditions. And that means that t at x equals 0 is t of naught, t at x equals L is t of L. So I can check it here. I can see that it happens. So you can see here in our example that, and let me remove all these lines so it's a cleaner presentation for you guys. But you can see here that phi naught, this is phi naught. If I plug in x equals 0, I get t naught. So this works out. If I plug in phi x equals L, this cancels out, I get TL. So this works out also. You can see that phi naught took care, phi naught, the purpose of T naught was to take care of the inhomogeneous boundary conditions. And then the rest of it needs to satisfy the homogeneous form of the boundary conditions. What that means is that at x equals 0, phi has to be 0 because t was specified. and then x equals, and this phi 1, this phi 2. You can see here that phi 2 is also 0, both at x equals 0 and x equals L, because t was specified. So now that I have this form ready, all I have to do now is plug in this t tilde in here and let Mathematica do the work. So take the first derivative of I respect to a1, set it to 0. Take the first derivative of I respect to a2 equal to 0. You'll get a system of equations like that. Something like that. And it's a conservative differentiation not conservative differentiation process, but it's a conservative problem. So the system, the matrix will be symmetric. We talked about that. So if a functional describes a conservative system and it has a self-adjoint, the stiffness matrix will be symmetric. You can invert this. Sorry, that's a wrong way of inverting. You can invert this matrix, and then you can find A1 and A2. Once you find A1 and A2, I apologize. Once you find A1 and A2, you found the approximation function T tilde, and the approximation T tilde is the one that does the best it can to minimize or maximize that functional. It also solves the governing equation that's implied by this functional, which I'll show you what it was if my computer cooperates. And I apologize for the number of problems that we encountered today, but I hope it's clear what we're trying to achieve. This is the governing equation that we were talking about. So that approximation function does its best to approximate a solution to this particular problem. To me, this is very exciting lecture, because you'll be waiting all along for this. How can we be smart? Instead of solving these differential equations that have very complex solution at times, what if we approximate a solution and just do good enough? And if I'm able to do that, perhaps I can solve more complicated problems like the partial differential equations, which is 15 unknowns, 15 equations, and solving them for the whole aircraft. Wouldn't that be amazing? And why solve it exactly? You cannot even do it exactly. So we can solve it approximately, and that's the basis for what we're trying to do. And so, yeah, just before we finish this lecture, let me just summarize what we've done. We have a functional I. If I render I stationary, I get governing equations for this problem. And in W, say. And here I depends on W. So the W that minimizes or maximizes I is the one that solves the governing equation. So that's the exact solution to the problem. But instead, what we said is forget about that. Too much work. Approximate W instead. Come up with W tilde. And that W tilde has phi naught. And these are the only unknowns now. This phi naught only satisfies the inhomogeneous form of the essential boundary conditions. This makes sure that it satisfies the homogeneous form of the boundary conditions, that it is linearly independent, that it is complete set of functions. You're not skipping functions. For example, I didn't skip functions in my previous example. I didn't go 1, 2, and then here I went 3 and 4. I didn't do that. I didn't jump terms, right? So we don't want to do that. And so, yeah, so, and you can add more and more terms, but all that's going to do is cost more work, although the computers will take care of that. Plug in W tilde, plug in W tilde in I, and now I becomes a regular function. And that does not read like regular function. And now I only depends, so now this becomes I tilde. Now I tilde only depends on A1, A2, blah, 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 blah. And to minimize I or maximize I, you guys already know how to do that from calculus. Set each of these derivative equal to 0. There's n equations, n unknowns. You get a stiffness, some sort of matrix, doesn't have to be a stiffness. And now you can solve for a linear system of equations. Invert this, find A's. Once you find A, you find W. With not only W minimizes or maximizes I, in most likely minimizes if a function don't exist, but it also solves the governing equation. It does its best it can to solve the governing equations. So that to me is very exciting, and we'll be covering a little more of that in a second lecture.